Artificial intelligence refers to computer systems designed to perform tasks that typically require human intelligence. These intelligent systems range from simple rule-based programs to complex neural networks that can recognize patterns and make decisions. AI systems are designed to perform various tasks, including learning, reasoning, problem-solving, perception, and understanding language. Modern AI exists on a spectrum, ranging from simple rule-based systems to complex neural networks that can process vast amounts of data. AI systems are categorized into two main types: narrow AI, which is specialized for specific tasks, and general AI, which would theoretically be capable of performing any intellectual task a human can do. While narrow AI is common in our daily lives, true general AI remains theoretical and is still an active area of research. Neural networks are organized in a layered structure that processes information hierarchically. A typical neural network has three types of layers: input, hidden, and output. The input layer receives raw data, hidden layers process this information through weighted connections, and the output layer produces the final result. Information flows through the network from the input layer, through the hidden layer, to the output layer. As data passes through each connection, it's weighted differently. Each neuron in a neural network processes information in a similar way. Inputs are multiplied by weights, summed together, and then passed through an activation function. The activation function determines whether a neuron should be activated. Common functions include sigmoid, which squashes values between 0 and 1, and ReLU, which outputs the input if positive, otherwise 0. Deep neural networks contain multiple hidden layers, allowing them to learn increasingly abstract representations of data. This hierarchical structure is what makes deep learning powerful. The first layers detect simple features like edges and corners, middle layers combine these into shapes and parts, and deeper layers identify complete objects or concepts. This hierarchical structure enables neural networks to tackle complex tasks like image recognition, natural language processing, and game playing, which require understanding at multiple levels of abstraction. The AI pipeline transforms raw data into actionable decisions through several processing stages. This pipeline includes 5 key stages: data collection, preprocessing, feature extraction, model training, and inference. Data collection is the first stage, where raw information is gathered from various sources like sensors, user interactions, or databases. In the preprocessing stage, raw data is cleaned by removing errors, handling missing values, and normalizing the data format. Feature extraction identifies the most relevant patterns and attributes from the preprocessed data, transforming it into a format that the AI model can learn from. During model training, the neural network learns from the extracted features, adjusting its internal weights to recognize patterns in the data. Finally, in the inference stage, the trained model processes new data to make predictions or decisions. Let's take a closer look at the inference process, where a trained neural network transforms input data into decisions. During inference, input data enters the neural network through the input layer. The data then flows through hidden layers, where each neuron applies weights and activation functions to transform the signal. Finally, the output layer produces the network's decision or prediction based on the accumulated transformations. In practical applications, the AI pipeline transforms data into valuable decisions across many domains. For image recognition, the pipeline processes raw image data through the neural network to identify objects with high confidence. Recommendation systems use a similar pipeline to analyze user behavior and product data, transforming it into personalized suggestions. In summary, the AI pipeline is a powerful sequence of transformations that converts raw, unstructured data into valuable, actionable insights. Despite impressive capabilities, current AI systems face significant limitations. AI systems require massive amounts of data and computing power. Training state-of-the-art models can consume enormous energy, making them environmentally costly and inaccessible to many. Neural networks can amplify biases present in their training data, leading to unfair or discriminatory outcomes. These systems mirror and sometimes magnify societal prejudices, especially when developed by non-diverse teams. Neural networks lack true understanding and reasoning abilities. They excel at recognizing statistical patterns but have no conceptual comprehension of what they're processing. This makes them brittle and susceptible to manipulation. AI systems struggle with causality and common sense reasoning. They can't determine what causes what, often confusing correlation with causation. They also lack the intuitive understanding that humans develop from experiencing the physical world. Neural networks struggle to explain their decisions. Their internal workings are often opaque, creating black box systems where even their creators cannot fully explain how specific outputs are generated. This raises serious concerns for trust and accountability. These limitations highlight the significant gap between current AI systems and human intelligence. Despite remarkable achievements in specific tasks, today's neural networks fall far short of the flexible, generalizable intelligence that humans possess. Artificial intelligence research continues to advance at a rapid pace. The future of AI and neural networks is focused on several emerging directions that will shape how these technologies evolve. First, researchers are developing more efficient architectures that require less data and computing power. Self-supervised learning is another important direction, allowing AI to leverage vast amounts of unlabeled data by finding patterns without human guidance. Multimodal models are becoming increasingly important as they can integrate different types of information such as text, images, and audio for more comprehensive understanding. Explainable AI is becoming crucial as these systems make more important decisions. Future models will be able to justify their decisions in ways humans can understand. Neuromorphic computing aims to create hardware that more closely mimics the brain's efficiency and processing power. While artificial general intelligence remains distant, neural networks will continue evolving to solve increasingly complex problems. The future of AI will be characterized by systems that are more accessible to developers, more efficient in their operation, and more trustworthy for end users.